Now let's first remember the cosine function. Cosine function is 2 pi periodic. So if this is cosine t, then this point should correspond to 2 pi. Let's make this cosine function an integer number periodic rather than 2 pi periodic. So let's make this point 1, and then this will become cosine 2 pi t. Let's make it even simpler, and instead of using integer numbers, let's use a symbol for period. Let's call it capital T. So this cosine is capital T periodic. Therefore, this function will be cosine 2 pi t over capital T. Now let's see another cosine function which is more frequent than this one, exactly 2 times more frequent than this cosine 2 pi t over capital T, which is this function. And the formula for this cosine would be cosine 2 pi over capital T times 2t. As you can see, it repeats itself for 2 times, 1 time here. Therefore, we have a 2 inside this cosine. Now, if we have a more generic formula for cosine, we can say that if a cosine repeats itself for n times in between this capital T period, then its formula would be cosine 2 pi n times t over capital T. Okay, now let's remember the integral of cosine. So if we integrate a cosine function over a period, this portion will cancel out negative portions. Therefore, the integral would be 0. Therefore, if we integrate a cosine function over a period, that would be a 0. If we use the generic formula that we have obtained, 2 pi n over capital T times t dt, that would be also 0. Now, okay, this function is pretty generic, but we can make it even more generic by letting imaginary part enter into the function. And this function would be e to j t, which is equal to cosine t plus j sinus t. Let's put this frequency component to it to make it 2 pi n over capital T. Here, same, e to the j 2 pi n over capital T. This function is actually periodic. If you want to visualize it, you need to imagine a real axis and an imaginary axis, and of course we will have a t time axis. But let me show this graph in MATLAB. A symbolic variable time t, and corresponding to real part I have created cosine t, and sinus t corresponds to imaginary part. Now if you plot, you will see that result is actually looking like a spring. Now if I rotate so that we face towards real axis and t-axis and we don't see imaginary part, now as you can see, that turns into a cosine. Now if I rotate again to look from in front of imaginary part, and real axis will vanish, as you can see, this is a sinus. So therefore this function is also periodic, and its integral over a period is 0. Why is it 0? If we look at from the t direction, we will see a circle. Now area under this circle is 0. Top part is positive, bottom part is negative, so the area, which is the integral of that function over a period, will be 0. Now let's see e to a 2 pi 2t, which we expected to repeat for 2 more times in between 0 and capital T. And it is shown as red line. As you can see, our original function, blue function, repeats itself only one time over period capital T, but red one repeats itself for 2 times. But again, integral of that 2 times more frequent function is 0. Now let me show a bit more interesting one. How would it look like if you multiply e to j 2 pi t and e to j 2 pi 2t? Well, mathematically you can easily obtain that result will be actually e to j 2 pi 3t. Therefore, we expect it to repeat itself for 3 times. This is exactly what we see here. The green line shows the result of e to j 2 pi t times e to j 2 pi 2t. If you rotate it along other axis, as you can see, actually this is also a spring. Note here that if you multiply two periodic signals in this form, their integral will be 0. That's an important fact that we use while deriving Fourier series. Now we know that complex exponential e to j 2 pi over t times n times t, its integral over a period is 0. But also, if you multiply it with another complex exponential with a different n, in this case I will call it m, e to j 2 pi m over capital T times t. We know that any of those multiplications over a period t would give us 0. But there is only one exception to that, and it is if n is equal to minus m, or let's change this sign to minus. In this case, if inside of this parenthesis is the same, then the result will not be 0. Therefore, this equation equals to 0 if m is not equal to n. This fact plays a central role in Fourier transformations. We call that set of functions orthogonal functions. Orthogonal functions has a property of having a 0 integration when we multiply them. So from a to b, phi n t times phi m t dt is equal to 0, where m is not equal to n. But if we add one more property to it, say if m equals n, then this multiplication will be non-zero, and if that non-zero result is equal to 1, then we call them orthonormal functions. And that means integral of phi n of t times phi n of t is equal to 1. So let's go back to our formula here. Now to make this formula orthonormal, we need to have this result of that integration to be 1. So when m equals n, inside of this integration would be e to 0, which is equal to integration of 1 dt, which is equal to t. Therefore, if you multiply both sides by 1 over t, then that integration will yield 1. Therefore, our new formula would be 1 over t times integration of two complex exponential functions. Now we will talk about why this function is important.